Hey everyone, so we have been solving exponential functions or exponential equations, and now we're looking at a couple more. And these next problems are also exponential equations, but they're slightly harder because they have more than one exponential term in the equation. So let's see how we can tackle this one. Question number one, we have e to the x plus 5 equals 7 times 2 to the x. Now, because we have exponentials on both sides, there's not really much we can do except try to isolate at least one of the exponentials. And fortunately, this one is already isolated. So I can at least simplify this by using, since it's base e, I'm going to use natural log on both sides. And so natural log of e to the x plus 5 gives me this, x plus 5. And then the next expression. Now, this is an error. I'm going to do it in red. I'm telling you it's an error, and I want you to analyze my mistake. I see an exponent. I'm going to throw the exponent as a multiplication out front. And I'm telling you ahead of time that's an error. I want you to think carefully about that. Why is that an error? The log property says if you have log base b of m to the x power, you can write it as a multiply of the exponent in front. So how come my statement is an error? It has to do with the base. The base is alone. Here, the base is not alone. I have a 7 multiplying it, so that x is only on the 2, but this is all messed up. This exponent law, the green one, doesn't apply. I cannot use it on this problem because of that 7. However, there is another law that applies, and that applies when we have a multiplication inside. We can separate the multiplication inside into the addition of two logs. And we're going to need to do that to separate the exponential 2x away from the 7. So we're going to use this second property to help us move forward here. And now we're good to go. So I can rewrite this as ln of 7 plus ln of 2 to the x. Now notice the exponential is alone. And then I can use the other log law to simplify this even more. So I'm going to have x plus 5 equals ln of 7 plus x times ln of 2. So that we use two log laws to help us simplify this expression a lot. We have another step to deal with now. We have x on both sides, and we need to collect our x terms. So I'm going to minus this x on that side and put all the x's on the right. I'm also going to minus the constant ln of 7 on both sides. So these are gone and those are gone. And that allows me to simplify my equation a lot. I have x ln of 2 minus x. So at least all the x's are on one side now. I still can't solve with two factors of x, or two terms of x. But we can do a really simple little algebra principle of factoring. And when I factor out these x's, x divided by x is 1. I have a product and I have one factor of x. And now it's really easy to solve. I'm just going to divide by that whole group. So this group cancels with that. And I'm going to put the x in the front, but I'll have 5 minus ln of 7 over ln of 2 minus 1. And that gives me an exact solution. Now, if we needed to check that solution for some reason, we could put that in the calculator and go from there. These next two I will solve also, but I have special slides for them, so those are gonna. So I have plenty of space coming for these. So let's take a look at that second one. And something similar to the last one in that it has two exponentials in it, one on each side. One is base 3 and one is base 4. Now in the last problem, I had one that was base e and one that was base 2. So at least natural log simplified the base e really nice. But in this one, I have a base 3 and a base 4. Nothing really nice is going to come of this. I mean, as far as a quick simple log to use. So I'm just going to use a standard common log on both sides. And we'll have 3 to the 2x minus 1 and 4 to the 3x. So log base 10 will not undo exponential base 3. So these guys aren't really simplifying. However, I can still simplify with the log laws. I'm going to put the exponent. Now, I'm going to do that idea again. I'm going to write an error here, and I want you to find my error. Here comes the error. X minus 1 is an exponent. I'm going to pull it out front times log of 3. Now if you have to, pause the program and pause the video and study this and figure out what's my error. And I hope you're seeing it, but the error is that the exponent as a whole must be multiplying, and right now I'm just multiplying log times 1, and what I really need is parentheses because it is the log times both. So the error was not having parentheses when I multiplied that. I just put that in there because it's a common mistake for a lot of students when they first start working with these guys. So it is a group 2x minus 1, the whole exponent times 3, and 3x also is a group times log of 4. Now the expression on the right isn't such a big deal because there's no subtraction, so I don't have to distribute. But on the left, that is crucial. So speaking of distributing, I'm going to distribute, get rid of those parentheses. 1 times log 3 is itself, and 3x log of 4, these parentheses weren't really doing anything. Okay, similar to the last problem, I got x's on both sides and I need to clean that up. So I'm going to minus this term and move it over to the other side. Now I wish those were like terms, but they're not. If it was only 3x and 2x, they would be like. But because they have this extra factor, log 4 times log 3, that makes them not like. So unfortunately, I cannot subtract. I'm going to have to bring everything down here. 3x log 4 minus 2x log 3, and similar to the last problem, I still have two factors of x, but that's easily solved by factoring again. And so I can factor out, I got a single factor of x, and I can go from here to do the next step and just divide by this entire group. So that group cancels completely, and I have to divide it on the other side. And so in the end, I finally got a solution. X is going to equal negative log 3 over 3 log 4 minus 2 log 3. Now, just as a little tip or advanced heads up here, if you're checking the answer in the back of the book, or if you're in the software and you're checking the answer and it's not exactly like that, it could have to do with the negative. So theoretically, I could multiply a negative on the top and the bottom, and that would give me an equivalent answer, positive log 3. And a negative times the 2, I'm going to put it in front. It's positive 2 log 3 now, and a negative times the 3 will make negative 3 log 4. So the green one and the blue one are equivalent solutions. It's just that they have their signs switched around. So don't let that throw you off if you're doing this answer and the book has one way and you have another. Those are both equivalent solutions. All right, I got to set up to solve the third and the hardest of the examples that involve solving exponential equations. And this one is quite challenging, and it requires a little bit of insight, something that, to be honest, I'm not going to test you guys on this one for if you're in my class, but some people may be watching this that want to learn more, and some pre-calculus classes actually would teach this kind of problem. And it involves realizing that there is sort of something similar. It's sort of similar to a quadratic equation. And I'm going to show you a trick or a strategy here that is used quite often in calculus. It's called the substitution strategy. What I'm going to do here is, first of all, begin by noticing that this one is second power because it is like e to the x squared. Excuse me. And then this one is first power because it is just e to the x. So this problem is very similar to a quadratic equation where I have second power and first power. And that takes a little bit of practice and insight starting to make those associations. But one of the things that we're looking for is like a quadratic equation. We might see, I don't want to use x because we already have x's, but what if we had u squared minus 3u equals 18. Now this would be solvable to us because it's just a quadratic equation. We could probably come up with a solution. And the trick is realizing the pattern or the configuration matches. And here's another way that we can match up the configuration. If we can set u equal to one of the variables, and I'm going to use the first power e to the x, then I want to check, what is u squared? Well, if u is e to the x, then u squared is e to the x squared, which is e to the 2x. And I have a perfect match on both of my variable factors. This is like u, and this is like u squared. So this takes this hard problem and allows us to convert it into something that's not so hard. It's going to be tough, but if we take this and realize, okay, that's like my u squared, and this one is like u, now I can solve an equation that's way easier to solve. And so this is called the U substitution, and use this strategy in calculus to do problems often where you've got something that's too hard to do. And with this little substitution, it becomes easier to do. Now that we've got this u squared, this is like quadratic equations. And we know we can solve quadratics if we can make them equal to 0. And I'm going to minus the 18. It equals 0. And now I could either factor or use the quadratic formula. And fortunately, this one factors. And I get two solutions, u equals 6 or u equals -3. Now I'd be done if I were solving for u, but I'm not. I'm solving for x, so I have a little bit more work to do. What is u? I'm going to switch back now to my x solution, so I substituted in u at first, but now I'm going to switch back to what I really need, e to the x equals 6. Or switch this one back, e to the x equals -3. So I have two equations to solve for x, but because of the u substitution, it boiled down to two simple equations. So I'm going to solve both of those over here. Number 1, e to the x equals 6. And that's easy to solve because I can do a natural log on both sides. And so I get x equals ln of 6. And when I solve the other one, I'm going to plug in e to the x equals -3. Now, intuitively and algebraically, I'd like you to see something going on here. E is a positive number. If you take a positive number with a power, can you get a negative? No, never. Because if you have a positive with a positive power, you get a positive number. If you have a positive number with a negative power, you get a reciprocal, but it's still positive. It's always positive. This equation is impossible. It has no solution. Now that was kind of an intuitive discussion there. Algebraically, if we did it, well, we'd do like we've been doing the algebra all along. We do natural log. And we'd put in e to the x and -3. And this would simplify down to just x. And then we do the natural log of -3. Now you may remember the domain has to have a domain that's positive. And you put that in the calculator and you're going to get an error. So whether we do this intuitively or algebraically, we're finding out that this one does not exist. So I don't have a solution to this equation. I only have one. And it turned out to be the natural log of 6. Now, I'm kind of curious. This was a very complicated equation. Does that really work? Well, we have a couple ways we can check this. So let's go over to the calculator and check this. Let's do a natural log of 6 just to get a decimal round off. And it's about 1.79. And now let's graph the equation. Now I've already set up the graph just so we can save time a little bit, but you can see I put in e to the 2x power minus 3e to the x power as my left side equation, and 18 is my right side equation. And my window, since I'm talking about 1.79, doesn't need to be too big, but I put -5 to 10. Now, we already know the domain can't be negative from that discussion down there, so I could have easily gone 0 to 10. And my y, biggest y is 18, so I made it go up to 20 here. Let's graph this and see what happens. And sure enough, we're only seeing one solution. If we had 18 going across and there were two solutions, we would need to see something like that, or we got two different solutions. But that's not what's showing up. There's only one solution, and let's check it. Go to second trace button, number 5 to do the intersection. And I've got a point highlighted for my first curve. I'm going to enter that. Second curve, enter that. And the guess, I'll just use that point as my guess. And it's calculating 1.79. That 1.79 is matching my algebra over here. So now I got confirmation that I got a solution to this equation. So that's it for our exponential equations, and that's one that's much tougher than I think you're going to see in my class. But anyways, I do have a couple more log equations to solve with you, so check in the playlist to see the next couple of problems that come up.